And anybody hear me?
Yes, we do.
Yes.
Okay, great. Save that. All right, so tonight we are continuing from our discussion on thermal stresses, thermal strains, and how do we solve for indeterminate structures under thermal stress. The determinate structure, we did that, a quick example. Those are fairly trivial. Just how much does something expand or contract with temperature change is a fairly simple equation. But what do you do when you have something that is restrained? It wants to expand or contract and it's not allowed to. How do you then solve for those problems? So we started that Tuesday, and we got through example number 2, which was 2 different material rods wedged between 2 walls and went through a temperature change. Now we're going to take a look at example number 3 and continue on the discussion. Before we get started, does anybody have any questions for me with regards to what they've read or the homework or just anything in general? Okay, then let us continue. Okay, so then we're going to move on to the next level of complexity with example number 3. For example number 3, we have a restrained bar as shown. Okay, so this time we have some material from A to B, a different material from B to C, but we have this gap in between them. So this little gap right here actually allows the material to expand somewhat before it comes into contact and starts building up restraining forces. So how do we deal with this gap in solving this problem? Okay, so the material is going to be from A to B. We're going to use a copper. If I remember right, these values are not from the back of the book. I just kind of invented them just to change things up a little bit. So these are slightly different than what you would find in the back of the book. But for this particular problem, we're going to say the copper has a Young's modulus of 15,000 KSI. Alpha is 9.4 e to the minus 6 over degrees Fahrenheit. The area is 1.227 inches squared. From B to C, we are dealing with aluminum. Young's modulus is 10,000 KSI. Alpha is 13 e to the minus 6 over degree Fahrenheit. And the area is the same at 1.227 inches squared. The starting temperature is 60 degrees. Our ending temperature is 400 degrees. So what is required? What are we trying to do here? We want to find the induced force in the rod from thermal expansion. So once this thing expands, comes into contact with each other, and then continues to heat up, what is the forces locked into these from that thermal expansion? Okay, do I have any questions about the setup? Okay. So we're going to, again, use the compatibility method to find our restraining forces. Break each member into individual free sticks and find the thermal deformation of each. So this is very similar to what we did on the last example. Delta T is T2 minus T1. So delta T is a positive 340 degree Fahrenheit. And for our first piece, A to B, we want to find what delta due to temperature for A to B would be if it was free to expand. So delta TAB is alpha times delta T times L. So our alpha times our delta T times L gives me 0.0384 inches. For B to C, my expansion there wants to be my alpha times delta T times L is 0.0265 inches. So here's where the difference comes in. The total restrained deformation is how much AB wants to expand delta TAB plus how much BC wants to expand TBC minus the gap between the two. Because what we're looking for is the restrained deformation. We're looking for how much did it want to grow and it could not grow. Well, we take the gap out of there because the gap allows it to grow freely unrestrained. So that's how we solve this. It is the total expansion of AB plus the total expansion of BC minus the gap between the two. So that gives me 0.384 plus 0.265 minus my 0.1 inches for a total restrained movement of 0.549. Okay, everybody clear on that, or do I have any questions? Okay, so delta T 0 equals 0.0549 inches is how much rod ABC would expand if it was free to do so. So now we find our restraining forces. So there is going to be some force in AB at B, that's R for restraining, that is going to cause a deformation delta RAB. So the equation, force is equal to delta AE over L, delta AE over L. So I plug in what I know. I have A, I have E, I have L. That gives me 1533.8 kips per inch times delta RAB. So that's going to be the relationship between the deformation due to the restraining force and the restraining force itself. For member BC, I have the same restraining force, and that causes delta RBC. FBR, or B, yeah, FBR, again, is equal to the deformation times the area times Young's modulus divided by L. But this time it's all the numbers from the BC side, and that gives me 2045.0 kips per inch times delta RBC. I now have an equation that relates these two together because I know that delta RAB plus delta RBC, the two restraining deformations plus the total that it wanted to expand in the first place all equals 0 because the overall length can't exceed the beginning overall length. So the net expansion plus the net contraction due to restraining forces brings it back to the original 0. So I can plug in what I know, RAB plus delta RBC, and I pull this to the other side is minus 0.0549. Equating for FBR, FBR is 1533 delta R, I just repeated this here. FBR is also 2045 delta RBC. So therefore, the relationship between delta RAB and delta BRBC is that delta RAB is 2045 over 1533.8 delta RBC. So they are proportional to each other, to 1.333 delta RBC. Okay, so I repeated this equation, only now instead of delta RAB, I plugged in 1.33 delta RBC plus delta RBC is all equal to minus 0.0549. And now I can solve. I have one equation, one unknown. Delta RBC is 0.0235 inches. And since RAB is 1.333 times delta RBC, then I can say that delta RAB is 1.333 times minus 0.0235 gives me minus 0.0314 inches. And now that I have these deformations, I can solve for the force in the bar. I could have used either equation, the 1533.8 or the 2045, but 1533.8 times delta RAB, I plug in delta RAB, I get minus 48.11 kips. And the negative course tells you that this is in compression. Okay, so in the final condition, the temperature increase was enough that these two rods expanded, closed that gap completely, pressed up against each other, and induced 48.11 kips of compression into this system. Any questions about that? Okay. Remember that I know that a lot of these examples, when they're pre-worked out and I'm going through them on the screen, and I'm basically describing what I'm doing as I'm going through them, could either make sense or you just haven't read that far enough along that you're basically just taking my word for it. So when you get to these types of problems in the homework, if all of a sudden now it doesn't make sense, please remember I have office hour for 4:30 to 5:20 before each class. It's a Zoom, so you can just log in on the Zoom and ask any questions that you like. Okay, so now a question might come up. If the ends of these two bars have pressed against each other completely, then what would the final length of LAB be? What is the final length of LBC? How would I solve for those numbers? Because some of that gap got encroached upon by member AB, and some of that gap, the rest of that gap, was encroached upon by member BC. They both came together towards the middle until they came into contact. So how would I solve for those final lengths? So the answer is the segment length equals the original length plus the unrestrained expansion minus the restrained deformation. So we started like with AB, we started with 12 inches, and then we calculated how much it would have expanded if it was just left alone and there was no restraint at all. And then what we just calculated was how much this 48.11 kips of load caused it to shorten. So if we add all that together, we will have its final length. So its final length is the original 12 inches. The 0.0384 is the uninhibited expansion due to temperature change minus my restraining, my delta due to the restraining force here of minus 0.0314 inches, and that gives me 12.007 inches is the final length of LAB. I can do the same thing with LBC. I can take the 6 inches of the original length plus the uninhibited expansion minus the restrained force, the restraining force that tends to contract it here, and you add these three together, you get 6.003. Does that make sense? Is anybody there, or is my headset not working?
Excuse me, Professor.
Okay,
So,
I can hear you.
yeah, should we add them? Because when you say minus times minus is plus.
Where's
Or,
the times? I'm sorry, you lost me on the question. Which minus, which times?
here you said like segment length equals original length plus unrestrained expansion minus the restrained deformation.
Yes.
So this is always minus, or it should be plus.
Okay. Okay. Well, thank you for asking that question. Let me try to explain it. If this is the original rod, okay, so the original rod was 12 inches. So there's the 12 inches, okay? And then due to the temperature change was a positive 340 degrees. So if I took this rod, just AB alone, and I increased the temperature by 340 degrees, then it will expand. And it will expand, we calculated, by 0.384, okay? So if it was totally unrestrained, then its new length would be 12 plus 0.0384. That would be the total length, right? That's easy to see. But then we calculated that there's a restraining force on this. It was not free to expand all the way. And that restraining force we also calculated is in compression. So that restraining force is trying to make the rod shorter by some amount because its compression is trying to shorten that rod. And so this deformation, the red deformation, is what we calculated right here, minus 0.0314. So we're using the principle of superposition. The principle of superposition says to get the final answer on something that has a lot of different things happening, I can find the answer for each individual thing and then add them all together. So the original plus the expansion due to thermal minus, well, it's not minus, it's actually plus the compression due to the restraining force. Does that help?
Yes, of course. Thank you.
Okay.
Professor, I had a question. Is it okay if you go back to the previous slide, please?
Sure. There?
Yes. So I noticed over here you were able to equate the two forces resultant. I thought we're only supposed to do that when the material is the same, like the question before. So does that apply to all kind of materials, even if they're not the same?
Yes, it does. Yes, it does. And I'll explain why. Let me go up a few more slides. Okay. In this slide here, and this is just kind of a more like a conceptual idea, but if these two rods are both expanding due to heat and they come into contact, once they come into contact, they start pushing on each other. Each one wants to expand into the other material and they're going to resist that. So it's going to be an induced compressive force if they're trying to expand. If the whole problem was reversed and we're lowering the temperature, it's the same thing. It's just they would now be in tension if you had them welded together or they're connected. But sticking with compression, sticking with increasing the temperature, when these two expand to the point where they are touching each other, they start putting compression into the system. What I wanted to point out is that there is no other loaded force on the system. So due to the lack of any external forces, that is what tells you that the force in AB has to be the same force in BC because there's no other forces on the system. So for equilibrium at joint B, if I was to cut a free body diagram and just look at joint B, in fact, I can do that. And hopefully I'm trying to fully answer your question. But if
but now it makes me wonder, okay, if they're heating, they're expanding onto each other, which the force is the same. But what if they're contracting? Does that also mean the force is the same?
Yes. Okay, so let me answer that too. But here is a free body diagram of just the joint at B. And there's no external loading, so therefore this force has to equal this force. And I basically just chose to call each one of these forces FBR. So this is FBR, and I guess I did it again. Anyway, you get the idea, but this is FBR. This has to be FBR because there's no external loads. And now, okay, so then you just asked, the second part of your question was, what if the whole system is contracting? What if the temperature was getting colder, not hotter? Is your question?
Yes, correct.
Okay, so if the problem was exactly the way that I show it here, then there would be no induced forces in either of these rods. Because there's a gap here, that means rod AB could just shrink and rod BC could just shrink, and it would be fairly easy to just calculate what the new gap is between the two. It's just the opposite of what we calculated for the overall expansion. The contraction would just be the opposite. Each one of them would get shorter. And because there's a gap here, they're not connected, so there's no forces involved at all. They're completely independent and unrestrained. Now, if you're asking, well, what if there was no gap and these are connected, these are welded or somehow made to be one piece, and then you lower the temperature, well, then the whole problem set is exactly the same. You would go through the example exactly the same way. It would just be in a few key places, and I'll show you where those are. In a few key places, right here, gap would be equal to 0. There would be no gap. And here, delta TBC would be minus 340, so this would be a negative number. And delta TAB minus 340, this would be a negative number. So then you would get to this point right here. This one would be negative, this one would be negative, this one would be equal to 0. And you just run through the whole problem exactly like I did. And you'll end up with a positive number for FBR, the induced force, which means that the whole system's in tension. Does that make sense?
Yes, thank you.
Okay, great. So this part right here, that was a great question. This part right here, how do I know that FBR on AB is the very same FBR on BC? How do I know that these two are equal? And the answer is, take a free body diagram of joint B. There is no external loading, so they have to be equal to each other by equilibrium. Our next example, that won't be true for the next example. So I got to the end of this one. Oh, okay. This is where I left off right here. How do you know this is right? How do you know at the very end of all of this that you got the right answer? Well, the new length of LAB plus the new length of LBC ought to equal the total overall gap between the two walls, because the walls by definition cannot move, and so they better fill that. And so the total distance between the supports is the 12 plus the gap plus the 6 equals 18.01 inches. and the total distance of the total length of the two rods in their heated condition is 12.007 plus 6.003 is 18.01 inches. So they are equal. That's your confirmation that you got the problem right. Okay, so we're going to add another level of complexity for example number 4. But before I do, any other questions on this material? And I implore you, if there's anything that you can think of that's not clear now, ask me now. These homework problems do take this up another notch. They're a bit more challenging. So
I have a question.
yes, please.
So you said that if there's no gap and their intention, so bar AB and bar BC will want to separate to each other, right?
They're going to try to separate, but if
Yeah.
they're connected, then they'll induce tension.
Oh, okay.
Just like if you took a rod, and again, it doesn't matter if it's made out of one material or 2 materials or 3 materials. If you take that rod in your hands and you just try to pull it apart, there's one tension across that whole rod. And that tension is equal to whatever it is, the forces you're able to generate with your arms to try to pull the rod apart.
Okay, thank you.
Okay. Any other questions before we move on to, this is our last example, by the way, for thermal stress. Okay. Example number 4. Okay, so here we have a restrained rod as shown, but now I have introduced this external loading to add to the complexity. I did take away the gap, so this one doesn't have a gap, but this one does have an external force. And hopefully this will cement the ideas of the questions that were just asked and the answers that I just gave. Hopefully this will drive it home. Okay, so for this particular problem, I changed the materials again. I'm going with red brass from A to B. Young's modulus is 14,600. Alpha is 9.80 e to the minus 6 per degree Fahrenheit. Area is 1.75 inches squared. For BC, we're going back to aluminum. Young's modulus is 10,600, and alpha is 12.80 e to the minus 6 per degree Fahrenheit. Area is 1.75 inches squared. T1 is 300 degrees. T2 is 0 degrees. So for those who just asked those questions, here it is. This one is being reduced in temperature. It is restrained. It is connected at the center so that it can't pull itself apart. And it has an external loading applied at B. Okay, so now what we want to know is find the induced force in the rod from thermal expansion and from the applied loading. Okay, so before we start looking at the solution, intuitively, looking at the problem, would you say that the force from the loading and the temperature change, is the force in AB the same as the force in BC? Anybody? Okay, I got several no's. That is correct. The force in AB will not be the same as the force in BC because you have to maintain equilibrium at joint B. So if you did a free body diagram of joint B, there's a load applied to it. So the restraining forces cannot be equal to each other with this applied load on there. Okay, so how are we going to solve this problem? Well, I'll give you a huge hint. The answer, again, is in superposition. What is superposition? Superposition is taking a complex problem with several different things going on concurrently, and you break it up into individual problems, solve them to a point, and then add it all back together. That's superposition. Okay, so our solution, we're going to use again, the compatibility method to find the restrained deformations. We break each member into individual free sticks and find the thermal deformation of each. So here's AB. And AB is going to have a deformation due to temperature change in rod AB, and it's going to have some deformation from the force at AB. So I have two different components here now. And again, superposition, I'm separating them. One is due to temperature, the other one is due to force. Okay, so delta T, T1 is 0 degrees. Was that right? No, T2 is 0 degrees minus T1. That gives me minus 300 degrees Fahrenheit. So the change in temperature is minus 300. And delta TAB is alpha delta TL, which gives me minus 0.1058 inches. That's how far this thing would like to contract if it was free to do so. Delta due to the force AB is equal to, and the generic version of the equation is PL over AE. P is FAB, the force in AB. So the force in AB is a portion of the 6 kips. Okay, remember the problem that we did last lecture, 2 lectures ago. The problem we did looked like this, but without temperature change. And remember what we found was that of the 6 kips, 2.4 of it was in tension here and 3.6 of it was in compression here. Some of this load is resisted by AB, some of this load is resisted by BC. So FAB is the portion of the 6 kips that is in AB, and it's going to be constant. So you have a constant force over a length of L divided by AE. So I can plug in what I know. I know L, I know A, I know E. So I have delta FAB is the force of AB over 709.722 kips. Everybody okay so far?
Yeah.
All right. Anybody not okay? Anybody completely and hopelessly, utterly lost?
So on this point, do you know like if it's compression or tension?
I do not. But that is a good question, because what am I assuming here? I'm assuming it's in tension. So that's a good practice, that an internal load, if you don't know what it's going to be, assume that it's going to be in tension. So I did assume that. That's why this is positive, because I'm assuming that it's stretching this out. Okay. Now, anybody else who, and you can chat this privately. I won't yell your name out, at least not again, hopefully. But anybody hopelessly lost? Is there anybody just looking at this going, boy, I sure hope I can figure this out in a couple of weeks when the homework's due? Is there anything I can help with that? Again, I can't see you guys, so I can't see the people with the glazed over eyes. But is there anything I can stop and help with before we keep plowing forward? Okay, so a question was, how do you know to use the compatibility method? Do you use it every time? That's a good question. Um, the flexibility method and the compatibility method will both get you the same answer. If they're both used properly, they will both give you the same answer. Um, be honest with you, I had to choose. I had to choose one or the other because I simply just don't have enough time to go through problems this complex in the Zoom lecture and do each one of them twice. I guess I could have mixed it up by using flexibility on one of them and compatibility on the other, but this one was getting pretty complex. I just didn't have time to figure it all out using the flexibility method. So I used the compatibility method, and I know that one, or at least I know how to apply it and I know how it works. So I guess the answer to that question would be, if you're adventurous, rework my example 3 and my example 4 and try to do it with the flexibility method. And if you are not adventurous and you just want to know how to do this and get the right answer, then redo the way I did it and see if you can get the same answer. No, that doesn't mean that. Are you kidding? I love this stuff. Of course I'll give you complex problems on the test. I mean, I'm showing you how to do it here. It takes 10 minutes, then I'm walking you through every step. You guys should be able to knock this out in 5 minutes. Uh, I guess the proper answer to Raphael's question would be, I am not limited on the test to complexity. I am not limited on the test to giving you problems that are easy, but I am limited to giving you problems on the test that nobody would be able to solve in a reasonable amount of time. That's my limitation. Does that make sense? Particularly, Raphael, you're the one that asked the question. Does that make sense to you? Okay. Okay. All right. Shall we move forward?
Yeah.
Okay. I don't hear any objections, so let's keep moving forward. So this was the free body diagram and investigating rod AB, and I have 2 sources of deformation now. I now have a temperature source and I have a force base source, okay? Now let's go to rod BC, and I have the 2 sources again. I have the temperature base source, which is alpha delta T times L, which is 0.0922. I have a real number there. But I also have a force base deformation that is FBC L over AE. FBC is not equal to FAB. We don't assume that they will be equal to each other. They're not, but it's unknown at this point. So we're just going to call it an unknown, and it's FBC over 772.917 kips is this deformation. All right, so now for the compatibility part. The 2 segments are attached at B. They can't just pull apart and create a gap. They're attached. One segment cannot deform relative to the other. Therefore, all of the deformations have to equal 0. All of the shrinking due to temperature of AB and the stretching of AB due to force, plus the shrinking of BC due to temperature, plus the stretching of BC due to force, they all together equal 0, because there can't be any net change in position of B, or B from the AB side can't be any different than B from the BC side. So all of the effects cancel each other out overall. Now that I know this, then I can say that the negative deflection, the shrinking due to temperature, plus the expansion due to FAB, minus the temperature change due to temperature in BC, plus the stretching due to force in BC, all equals 0. So then I can just consolidate this, put all the known numbers on the right-hand side and my variables on the left-hand side, like so. So this is one equation, but I have two unknowns. And okay, and then I took this onto this side. So now I'm solving for FAB in terms of FBC. I'm just doing this one step at a time. And then I multiply each side by 709 so that I get FAB is equal to all of this. Since we have two segments, we can make two cuts. Okay, remember a couple lectures ago where we can make some cuts and take some free body diagrams? So I have two segments, I can make two cuts. Looking at the first segment from A to cut 1, I have FAB in tension assumed. I have the reaction AX, sum the forces in the X direction, RAX put FAB equals 0, so the reaction is equal to the negative of the force. That's all that one tells me. Can't get anything else out of that one. But looking at the second segment from A to cut 2, I have, now this FAB is here because I substituted it for RAX. I learned from the first cut that the reaction is the opposite of FAB. So I put in minus FAB here because of this. And then my cut is on the other side of the point load. So I put in my 6 kips to the right, and I put in my FBC in my assumed tensile direction, and sum forces. Summing forces in the X direction, I have minus FAB plus 6 kips plus FBC equals 0. And guess what I have now? I have two equations for two unknowns. I have the first equation that came from compatibility. I have the second equation that comes from stability or equilibrium. Two equations, two unknowns. Now I can solve my problem. Yes, I can substitute. So that's exactly what I'm going to do. I substitute for FAB, this equation here that I found for FAB, and the only variable in this kind of messy thing here is FBC. So I have only one variable in this whole equation, FBC, which means I can solve the problem. And so I do a little arithmetic. I multiply this out, and I multiply this times that, and I have the 6 kips and the FBC, and then I consolidate. So 1.918 FBC is equal to 134.525 kips. So FBC is a positive 70.138 kips. See how that washed out? It's really kind of neat how this all washes out. This is a positive number, and it should be because we reduced the temperature, which causes tension. So this is the force in BC in tension. Now to find the force in AB, we go back to our compatibility equation, and we can plug in FBC here, which is 70.138 kips, solve this, and I get 76.122 kips, again positive, again in tension. RAX is the negative of FAB. So RAX is minus 76.122, which means it's the opposite direction that I had assumed. So I put my left arrow on RAX. RCX is minus RAX minus 6 kips. This is just summing the forces. And I get 70.138 kips to the right. And those are the induced forces. and I box my answers, and there it is. So by reducing the temperature, what was it, 300 degrees or so? By reducing the temperature of a rod by 300 degrees, I have built into it 70,000 pounds in tension. That little 6 kips right there is a small portion of the overall load. Most of it is just the contraction of the rod. But you can see where the 6 kips comes in here and some change. So, any questions about example 4? Okay. And this is my last slide for the day. What happens if you do not allow for expansion due to temperature or contraction too? But this is a classic example of what happens when you do not allow for expansion. And this is a buckled rail. You can actually see the other rails about to buckle as well, but this is a buckled rail because this thing built up many tens or maybe 100,000, probably tens of thousands of pounds of pressure on it. And when you build up that much pressure, even though you can see all these ties are providing lateral support, it actually took those ties and it blew these bolts right off the ties. See, all those bolts are gone. That's how much force was in that thing. I don't know how much expansion that actually represents. How much it swayed to the side buckling. This thing may have only wanted to expand 1/4, 3/8 of an inch. Maybe that's what it wanted to expand. And this splice right here and right here didn't allow it to expand by 3/8 of an inch. So that's what you get if you don't let it do what it wants to do. Okay, so this concludes our thermal expansion topic, and I believe this actually concludes chapter 4. Let me get my text real quick. Yeah, this concludes chapter 4. So in your reading, you should be through chapter 4 now in your reading assignments. I've been trying to keep up with the handouts. So the handouts are roughly about where we are here. I'll check again and see if I need to post another one.
So we don't have to cover the 4.7 stress concentration?
4.7. It would be nice to read through that, but I am not going to. I don't think I've got any homework problems on stress concentrations. It's good to understand that. And it also reinforces what we talked about with St. Venant's principle, where you get a certain distance away from a disturbance and you get a normalized average stresses. This is talking about what happens when you're not a certain distance away and you do have stress concentrations. So yeah, 4.7 is an excellent read. It's 1, 2, 3 pages, and it's good for understanding. But I'm not going to ask any homework problems on 4.7. And then 4.8, 4.9 are completely optional. And that's it for that chapter. Yeah. So what we're going to do, the plan is when we re-meet on Tuesday, the next lecture that I'm preparing is all about geometric properties. So we're totally shifting gears. We're jumping from chapter 4 to, I think it's Appendix A, where we're going to talk about section properties. How do you find the center of gravity? How do you find moments of inertia? Things like that. So that's going to be our next lecture on Tuesday. And then we're going to have our first midterm on Thursday. So no, that's not the last chapter for exam 1. Exam 1 is going to be chapters 1, 2, and 3, not chapter 4. Okay, so I'm sure you guys are very curious. I intentionally kind of left a gap here so that we could talk about our first test that's coming up 1 week from today. And I will open it up. You'll have plenty of time if you have questions. But before we do, let me just talk about the ground rules. The test will be a Zoom lecture. So you just log into the Zoom lecture like you always do. But what I'm going to have prepared is, instead of a homework assignment, it's going to be a test assignment, and it will become available. The test will become available at 5:30. So you're going to log into Zoom so you can see me and I can see you, and you can actually ask me questions if you like while we're taking the test. I'll be here the whole time. So that part of it is on the Zoom, so I can see you and you can see me. But then you're going to, at your computer, go on to Blackboard, log into and open up the test, and you're going to take it on that screen. Now, the idea is going to be that there's going to be 3 questions. Each question is going to be a PDF file. So you're going to open up that file and see question number 1 or number 2 or number 3. You can have them all open on your screen if you like. And then you're going to solve those problems by working it out with pencil and paper on your desktop. I mean, physically, real where you're working, you're going to work them out with a calculator and your pencil and paper. And then when you're done working out, say, problem 1, and it's going to have like a part A, part B, part C. When you have the answers for part A, part B, part C, you're going to input those answers into the text box. So right there on the test, you're going to type in 20 kips to the right, or 50 psi, or whatever the answer is to each one of those parts. You're going to type in that answer into the text box for that problem. Then you're going to go on to the next problem. Open up the PDF, work it out with pencil and paper, and then type in your answer. Now, the test will automatically submit at 6:45. So you have an hour and 15 minutes to work the test. At 6:45, it will, yes, Raphael, it is next Thursday. It will shut down, and whatever work you have done, that's what you got. So you got to watch your time. And I'm telling you, you got to watch your time. That's probably one of the bigger challenges, is do not spend an hour on problem 1 and then realize you got 15 minutes to solve problem 2 and 3, because it is a timed test. Now, at the end of the test, once you hit submit, or once it submits it for you because you ran out of time, then you're going to take all of your written materials, you're going to scan them into PDF, and you're going to upload them to an assignment, like a homework assignment, that is labeled midterm 1. So there's going to be a midterm 1 test that you take during the window of time that you have, and then there's going to be a midterm assignment that you upload your PDF work to. Be sure that you do this. Make sure that you upload that PDF work in a reasonable amount of time, 15, 20 minutes, get it all together and scan it and send it up, so that a lot of these problems, the whole test is worth 50 points. So each problem is worth somewhere between 12 and 20 points each. Each problem is going to have 3 or 4 parts to it. That means each part is 4 or 5 points per part. And each part has 1 right answer. So if you just give me the wrong answer and I have no handwork to look at, then one wrong answer is 10% of your grade. And that is quite harsh. That's quite restrictive to just get slapped silly with 10% of your grade for one wrong answer. So make sure you put your answers in the text boxes and get that test submitted on time, but also make sure that you scan and upload all of your handwork so that I can use your handwork to find any possible partial credit. That's how this test is going to work 1 week from today. Now, do I have any questions?
Is it going to be open note, or can we only have the cheat sheet?
Yes, good question. Let me, I was trying to do something here. It is open book. So it is open book and one sheet of your handwritten notes. Your one sheet cannot be anything that is scanned, Xeroxed, photographed, printed out, anything like that. It cannot be worked out examples. It cannot be material, even the homework solutions that I have given to you after each homework assignment. You can't have those in front of you. The idea is that you just have one page of crib notes to kind of help you find where to find stuff, basic equations and whatnot, but no worked out examples. And most certainly nothing from prior classes or from students that you knew who took this class 2 semesters ago, nothing like that. So it's open book and one page of notes. Now the idea was with Respondus that you can't have anything on your screen because Respondus locks everything out, but we don't have Respondus now. So this is kind of going to be on the honor system, that what is on your screen really should just be the test. That's why I've always said that if you don't have a physical version of the book, that you should print out the sections that you're going to need through the test. I understand now that we're not using the lockdown browser, I suppose you could just access your digital version of your textbook on the screen, but you might still want to consider printing out the portions. Like I said, chapters 1, 2, or 3, just so that you don't have to switch through all these different screens and lose time while you're trying to take the test. So that would be my suggestion, but without the lockdown browser, I can't prevent you from using a digital version. Of course, the obvious, do not Google the answers. Do not email your classmates. Do not get on your cell phone or do anything else stupid like that. We are going to try to do the best we can to make this test as fair as possible. And by fair, I mean nobody gets to cheat. So if there's any suspicion of cheating, the test doesn't get graded. So I'm trusting on you guys. This is a very unique, what is that word everybody keeps using? Unprecedented. I'm so sick of hearing that word, but we're just got to do the best we can. Raphael, do we submit our one page of notes as well, like at the end of our page submitted on Blackboard? Yes, please. Thank you for reminding me of that. Please include your one page of notes with your handwork that you submit on Blackboard under the assignment called midterm 1. And again, there's going to be a test midterm 1 and an assignment midterm 1. The test is what you take during your time and you put in your answers and you submit it before you run out of time. The assignment is what you use to upload your handwork to.
Do you want us to do the test on the engineering paper as well, or should we just use regular paper?
It should be engineering paper, and it should be basically the same as the homework. I understand People are a lot more stressed during a test than during homework. But here's the rule of thumb. You as the student, you want me to be able to read your work. You really, really want me to be able to read your work. Because if I can't read it, I can't find any partial credit, right? So it is to your distinct advantage that I can read every single letter and number that you want me to. So if you put it on engineering paper, as opposed to lined paper or the back of Chipotle's napkin or something like that, then I can read it. And you want me to be able to read it. So you want to be able to write as legibly as you can. You don't want to scribble all over this thing. You do not want to flip the page over and write on the back, which absolutely does not come across on PDF. So that's kind of the rule of thumb. You want me to be able to read. Reasonable, yeah, sure. Pen might be darker and easier to read. So that's the rule of thumb, right? You want me to be able to read it so that I can find partial credit wherever I can find it. It should be one question per page. I am not going to deduct points on it like I do on the homework because I understand the stressfulness of a test. But again, it's all about me finding what I'm looking for to give you as much credit as possible. And the best way to do that is to organize the work so that it's easy to follow. Here's part A, here's part B, here's part C. Go to the next page, here's problem 2. The more organized it is, the easier it is for me to find what I'm looking for, the more it is to your advantage. Any questions on the material of the scope of the test? What are we being tested on?
Are you gonna put like a question from like the review of statics, so like the chapter 1 stuff, or no?
What are we being tested on? Yes and no. Mario, that was your question. The answer is yes and no. And what I mean by that, I am not going to have one problem that is just strictly a review of statics. I will not do that. But I'm going to have 3 problems that every one of them is going to be a review of statics, because if you can't find your reactions and you can't sum up your forces, then there's no way you're going to get the problem right. So chapter 1 was about how to find your reactions on a determinate structure. It was also about how to find forces in a truss. Remember, we solved the reactions for a truss. We solved for the forces in the truss using the method of joints. We also found reactions for statically determinate beams. All of that is wide open. You got to be able to do that in order to answer the questions of what it is I'm asking you on the test. Stephen, it is not necessarily a problem from each chapter, no. It is 3 problems that I hope really kind of reinforce what was important from all 3 chapters. But it may be all 3 questions from chapter 3, or it may be 1 question from chapter 2 and 2 from chapter 3, and everything in chapter 1, you have to know that in order to answer the questions from chapter 2 and 3. Does that make sense? Jose, apart from the homework, are there any practice problems we could do to better prepare us? That's a good question. I would go back and review the lectures that we have done up till now. Not the lectures where we started looking at axially loaded indeterminate. That was a few lectures ago. That's not, chapter 4 is not on this test, but look at the lectures that covered chapters 1, 2, and 3. And what I posted on Blackboard were the consolidated versions of the lectures. So they're only like, I don't know, what were they, 15 to 30 sheets each. It's not too hard to go through those. Look at the examples I did for you live during the class. That's the type of problems I'm going to ask. Look at the type of problems I asked for the homework. That's the type of problems I'm going to ask. So make sure that any example problems I've done for you live during the Zoom meetings, you ought to be able to solve those because I walked you through them step by step. And also look at the example problems in the textbook as they walked you through them step by step. And then you can kind of get a gist of what the scope and the material is based on what I thought was important enough to put into the lectures. Also, back to Raphael's question, what are we being tested on? Well, what you're being tested on is stress, right? We spent a lot of time talking about stress. And we have normal stress and we have shear stress. And we have, how do you find stress? Stress is a force over area. Okay, so we talked a lot about that. We also talked about stresses at an inclined plane. So you talked about components. Remember the block of wood where it had 600 pounds of tension on it, but then you could take a 40-degree plane and you have some tension, you have some shear. So we talked about that. Again, go back and review the lectures that we've done, give you a sense of what is on there. But stress was very important. I think stress was all of chapter 2, right? And then strain is very important. And strain, I think, was all of chapter 3. So we have normal strain, the stretching of a wire, or the compression of a cylinder, or even something that is warped in plane. You have corner-to-corner distances that could go through normal strain as well. And we talked about shear strain. We talked about shear strain quite a bit. So really, this first midterm is about fundamentals from statics, find your reactions, take a free body diagram, solve a truss, and then it's all about stress and it's all about strain. Raphael, I think I've said this like 5 times now. It's chapter 1, 2, and 3.
Have you already made the exam?
Maybe. Possibly. Why?
Follow-up question. You're not going to give us any problems from like the FE exam or something like that, right? I had a professor did that and it didn't go very well.
The FE exam?
Yeah, my fluids professor gave us problems from the FE exam saying that he was going to prepare us for it, and everyone that I talked to said they didn't do very well on it.
Okay. Okay, well, there's 2 perspectives to that. First of all, I took the FE exam when it was called the EIT exam, and I took that in 1994. So I have no idea what's on the FE exam, so not much chance of me doing that because I have no clue what's on it, in the last 25 years. But the other side of that is that this class, along with statics and fluid mechanics and thermodynamics and just dynamics, those classes are all the classes that prepare you to take the FE exam. So from your experience in this class, you should be prepared to be able to take the FE exam. If there are questions on the FE exam with regards to mechanics of materials that you can't figure out after you've taken this class, then I've failed. I haven't done my job. I haven't exposed you to all that you're supposed to know. So that's the other side of the coin. But I think the simple answer is, I'm so out of the loop, I don't even know what's on the test. So no, don't expect anything from the FE exam. Man, I just realized that made me sound old, didn't it? Okay, we still have 5 minutes. What else you guys got?
So you've said to like go over the examples in class and stuff. So will the problems on the test like be similar in structure to the ones you did in class and the ones we've done on homework?
Yes, they will. They will be similar in structure, but and similar in concept and similar in here's what's given, this is what I need. Or I might switch it up and say, well, here's what's given and this is what I need. But they're all stemming from the same handful of equations that are the basic principles, right? So we talked about Hooke's law. That's a real basic one. Hooke's law, stress is equal to strain times Young's modulus. We talked about what is stress? Stress is force over area. What is strain? Strain is the new length minus the original length over the original length. Those are the basic concepts. There's only so many ways that I can try to trip you up in a problem when we're only drawing from those very limited handful of principles. So yes, I am going to have them. They're going to be like what I do in class. They're going to be very much like what you do on the homework, but I do have to constrain them so that you ought to be able to solve each one of them in 25, 30 minutes. Some may be a little longer, some a little shorter, but there's a time element here. So I have to be cognizant of that. By the same token, when you are taking this test, if you happen to see a problem that looks just like a problem in the homework, and you know that problem in the homework took you 2.5 hours to work through, do not freak out, because it does not necessarily mean that I am asking for all the same things that the homework problem had asked you for, or there may be more information given to you that you don't have to struggle through from the homework. So again, my point is, if the problem looks like something in the homework that took you a long time to do not be immediately dismayed. It may be that I'm asking for different things or giving you different parts, and I'm only asking for certain things that should be doable in the time that you have. Keyword is should. If you have studied, if you have struggled through the homework, if you have gone back through the lectures and tried to do the examples that I've done for you, then they should be doable in the time that you have. I'm sure you guys are sick of hearing this, but I will say it one more time. If you, on the other hand, worked through all of your homework assignments by basically having the solutions manual open or somebody else's homework open, or I don't care what, something that you just copied from this to that to this to that. Oh, that makes sense. Oh, no, sure. Okay, that makes sense. All right. And it took you 5 minutes, 10 minutes to do each problem. If that was your way to solve the homework, then you are really, really going to struggle on this test and probably will not do very well at all. I've seen it semester after semester after semester. So that's my warning. Mario, do we have to draw the example from the test like we draw the figure from the homework? No, you do not. That's a good question. I am not going to grade you on what you have drawn. I'm not going to grade you on your drawing skills, but my suggestion is draw at least enough that you can get your hands around the problem. Draw the free body diagram for your benefit so that you can get your hands on this, right? But unless I specifically say, draw a shear diagram or draw the axial load diagram, or if I actually say draw something, then yeah, you better draw it. But if I don't, then it's really there for your use, not mine. Any other questions? It's about time. If you think of anything, of course, we can bring it up on Tuesday. Got one more lecture, and there's always office hours before each class. So the clock is telling me it's time, so why don't we draw this to an end? And again, if you have any more questions, you'll have another chance on Tuesday. So everybody have a great weekend. Study hard, and I will see you next week.
Thank you, Professor.
Thank you, Professor.
Okay, thank you. We'll see you next time.